Okay, so we are very pleased to have Matthias with us. Many of you heard the very nice published lecture he gave yesterday. Also for the students and postdocs, so he has agreed to, so after this is over, we have the room, so you can stay here, and if you want to have any questions on the talk or other things, if you generally want to interact with him, please stay in this room. Okay, so he's going to talk about weakly coupled light new physics.
Thank you. Thank you very much. Does this work without a microphone?
Yeah,
for you, and also for the Zoom. I need a mic. Okay. Great. So, for those of you who were there yesterday, welcome back. It's still a great honor to give these lectures. This is the second talk, Physics Colloquium. And you will see that the three lectures cover quite different topics, but the lecture today will have some overlap with yesterday, for those of you who were not there yesterday, of course. So weakly coupled light to particles is a theme that has been attracting more interest in recent years for a very pragmatic reason, that we have not discovered heavy new particles at the LHC, and therefore people got interested in an alternative of light new particles, and I think it's an interesting alternative. So that's the main topic of today, and then in the seminar tomorrow, we'll go really to high energy LHC physics with Jens. So if you were present yesterday, you know, of course, that the Standard Model is a fantastic theory of the microcosm. Really, everything we have measured at the LHC, but also at other facilities at CERN and elsewhere, can be described by this theory, with a few statistical fluctuations maybe, but nothing that's really significantly in conflict with the Standard Model. This again, as a reminder, the setup of CERN near Lake Geneva in the Alps, 27-kilometer ring, the Large Hadron Collider, about 100 meters underground. And the main experiments you see here, CMS is the one where India is participating very visibly. Atlas is the other general purpose experiment, and then an experiment for heavy ion physics and for flavor physics. Now, of course, these experiments, they have completed the Standard Model with the discovery of the Higgs boson in 2012. Covered this in my public talk yesterday. This is one of the events where most likely Higgs was produced, decaying into the photon. And that has completed the Standard Model as I have described it yesterday. Here is another picture of that with the 6 quarks. Can you see this? This is very faint somehow. The 6 quarks, the 6 leptons, the force carriers for the weak interactions, the electromagnetism and the strong interactions, and the Higgs boson. And many aspects of the Standard Model are very beautiful and very, in some sense, minimal. It is a mathematically consistent gauge theory. What we mean by that is that it's built on symmetries and it's renormalizable, it's predicted. There's nothing that you need to add to the theory to make predictions. To the best of our knowledge, all of these particles are point-like. They have no spatial extension. They are characterized by mass, charge, and spin, angular momentum. There are 3 generations of all the matter constituents shown here. A generation is the vertical column here. And for instance, the second and the third vertical column, these particles have absolutely identical properties as the one in the first generation, except for the mass. So all the charges are the same. The electromagnetic interactions are the same. The strong interactions are the same. The weak interactions are the same. And what is different is the Higgs boson interactions, because those are proportional to the masses. And then, as I explained yesterday, the mass itself is generated from spontaneous symmetry breaking when the Higgs field acquires a non-vanishing value in the vacuum. Now, this is a fantastically successful theory, but as I already mentioned yesterday, there are some things which it does not explain, some questions which it does not answer. And those questions I distinguished yesterday between observational facts and theoretical worries, so to speak. So observational facts come from the universe. When we do astrophysics and cosmology, we see that, we find that there's a lot of dark matter in the universe and even more dark energy. And there is no candidate for dark matter in the standard model. And dark energy is something having to do with gravity, so it's not even part of the standard model. And that's the main reason why we know that the standard model is not a complete theory of the universe. There's this question about matter and antimatter not being present in equal amounts, which is also not explained by the standard model, even though actually there's a mechanism called leptogenesis, which is a mechanism in the standard model the moment you add neutrino masses, which we know exist. So maybe there is even an explanation of the standard model. There's the so-called strong CP problem. I mentioned it yesterday. I somehow have a weak laser pointer problem, not a strong CP problem. Can you see the spot? Okay, good. The question how the weak scale is stabilized against quantum corrections from gravity, what explains the pattern of masses and mixing angles in the standard model, etc., and how to unify quantum mechanics with quantum. The last question we can ignore if we focus on particle physics. We don't need to worry about gravity. And then, for instance, the last three questions are really theoretical questions. It's not, there's nothing wrong in the standard model. We are just a bit confused why are scales so different. But you know, that could also be just a fact of nature. But clearly, dark matter is something that exists we want to describe. So, for the purposes of this talk, I will focus on light no physics. Why? Very simplistic. When we look for new physics, of course, we have something that we know, our standard model. We have reasons to believe there is more in physics not described by the standard model. And then, you know, there is at least a two-dimensional strategy for searching for new physics. Either we increase the energy of our collider and look for heavier and heavier particles. That's what has often been done in the past. You just build a bigger accelerator. If you're lucky, you'll find new particles. Alternatively, you can also, if you are in a position that you can easily increase the energy, you can also look more precisely. You can measure what we call position observables. I discussed one yesterday, the anomalous magnetic moment of the muon. It's super low energy. You don't need a lot of energy. But you just look at billions and many billions of muons, and you just do the measurement many, many, many times, so you get very, very accurate. I gave you an example yesterday where things were measured up to 10 significant digits, and that's also a way to look for new physics, okay? And of course, both strategies have been pursued, and so far, no compelling observation has been done. Sorry, but we can look at this plane where in one direction we increase the mass of the new physics. So here clearly we need, we can look for the effects of heavy new particles, which if we want to produce them, we need a lot of energy, but we can look for quantum effects of these particles. That's one strategy. The other strategy is to say, well, maybe the new particles are not heavy, maybe they are light. If they are light, we can in principle already produce them in our measurements, but maybe it's hard to see them because they couple very big. So for instance, the dark matter could be light, There's many models where dark matter is light, even very, very light, but you don't see it because it couples either very weakly or not at all, except for gravity to the standard model. Okay, so that's this axis here, where we are not at. Sorry, I cannot.
So when you're pointing it on the blue part, it's visible. It's just the white part.
I don't know why it's sometimes maybe I'm
Yeah. Is that the thing? Do you need a stick or something?
I may just use this old-fashioned. Okay, so I'm going to focus on this axis. Okay, so we have tried to find heavy new particles. We have not succeeded. So let's consider the possibility that new physics is light, but very weakly coupled. We actually have an example in the standard model, the neutrinos. Those of you interested in neutrino physics, when neutrinos were invented, people thought they will never be able to see them. In research, never works. So in the end, we always find ways of doing things, but it was very hard to find neutrinos experimentally because they really interact extremely weakly. Okay. So maybe there are other particles like the neutrinos, which are very light, but very weakly interacting. Now, this is a question which can be answered in terms of such a very light particle, the question about the strong CP problem. So let me discuss this problem in a little bit more detail. And now I hope that you have all seen Lagrangians in your university courses, so you know roughly what I'm writing down here. So what I'm telling you is that when we write Lagrangians for the different components of the standard model, the strategy is always. Is this a green one or? Yes. Okay. Wonderful. Yes, that is much better. Thank you very much. Thank you. So when we write a Lagrangian, we have certain rules, quantum numbers that must be conserved, symmetries that must be conserved. But once those rules are obeyed, every term that can be written is usually written down and should be there. If it's not there, it should be forbidden for a reason. And the point is that in QCD, the theory of the strong interactions, I'm not giving you the Lagrangian of QCD. It's here in the ... I'm giving you a term which, according to the building rules of the standard model, can be written down. It respects all the symmetries and it's gauge invariant, it's normalizable. So we could add this term to the QCD Lagrangian. Nothing prevents us from doing so. And in fact, it's even worse. If you're not writing down and you perform a redefinition of the quark masses, you can actually generate such a term. So it's not that even if you don't write it down, you can change the parameters in your theory and it generates this term. If you have such a term, it gives rise to what's called an electric dipole moment of the neutron. So you take a neutral particle, it doesn't have a charge. So an electric dipole moment means that somehow within the particle you separate, it's neutral, but you can separate a little bit of electric negative charge in one direction, positive charge in another direction. Then you get a dipole moment. You also have a spin, magnetic moment, and then if you perform a parity and a time reversal transformation, you see that this thing is odd. It changes sign under both, which also implies by the CPT theorem that it changes sign under charge parity conjugation. So it's a CP odd. It's a CP odd observable, this electric dipole moment. It violates CP, which in the standard model, besides this term, only the Kabibo-Kobayashi-Mascara matrix does. And now you just ask, do we have experimental evidence for this term? And the striking puzzle is that people looked for this electric dipole moment, and they found that only an upper bound, which is extremely small, 10 to the minus 26 times the electron charge times a centimeter. So that's very, very, very small. And if you convert this to a bound on this coupling, you get 10 to the minus 10. And the question is, you know, if we agree that by the rules of the game we should write down this term, why does it have a coefficient which is essentially 0, smaller than 10 to the minus 10? Normally, when that happens, we want a reason why it's 0. If it's 10 to the minus 10, it should better be 0, and if it's 0, there should be a reason why it's 0. Okay? So can one find a dynamical way to set theta to 0? Some field theory work, the field theory itself should set this theta to 0, and the answer is yes, one can. And this was actually figured out a long, long time ago, a few years after the standard model was established by Patrick, Queen, Weinberg, and Wilczek. And basically, the idea was, well, if this theta, we want theta to be small or 0, we can make theta a field. Instead of a coupling constant in the Lagrangian, we can make it a field, and then we can try to find some dynamics that puts this field to 0. So a potential for this field, which will have its minimum at 0. And that's what the so-called QCD axion does. So basically, you add to theta a field, that's the axion, divided by some dimensionful constant, Fa. And you could also, of course, now you can consider this combination, the field, to be the field, right? You can include this theta into the field A, and then you want that this whole coefficient has a potential that has a minimum at 0. And that actually miraculously happens by just writing down this equation. If you go through the low energy dynamics of QCD, you take this Lagrangian, you match it, for instance, to a chiral Lagrangian at low energy, you find a periodic potential which has its minimum exactly where this coefficient vanishes. And that's a really remarkable, beautiful solution to this problem that we are not seeing the electric dipole moment of the neutron. But it predicts the existence of a new particle. Now, the properties of these particles are very strange, and they are completely predicted by this mechanism. This is a scalar particle. It's actually, to be precise, a pseudo-scalar particle. The scalar particle has mass dimension 1. This is the reason why we need to put the scale here, Fa. Scale is called the Patrick-Quinn scale. And in fact, the way this field comes about is that at high energies, actually this Fa will turn out to be a large mass scale, and at energies as large as F or higher, actually what one writes down is a completely new scalar field, complex scalar field. And then, like in the standard model, with the Higgs mechanism, we break the symmetry. I told you yesterday, you have the Mexican head potential, you break the symmetry, and then the field has a vacuum expectation value, and it can perform oscillations about this vacuum expectation value. Same thing happens here. The axion actually corresponds to the degree of freedom of going around the minimum of the potential. And that happens at a large scale. So in the Higgs mechanism, the scale is the vacuum expectation value V, and here Fa is also a vacuum expectation value. But we can play with it. We can give it any value we like. And in fact, we have this beautiful relation that this axion gets a mass, and the product of the mass times the decay constant is related to the product of the pion mass and the pion decay constant. And those are quantities very well measured in QCD. And then there is a combination of quark masses which also enters. And you see that if you make this Fa a large scale, a scale beyond the standard model, right, because we haven't really seen this physics explicitly, so presumably this F is a large scale. The larger you make F, the smaller Ma becomes. Okay, nice relation. So this is shown here. This is Fa. This is Ma, the axion mass, as the function basically of the scale 1 over f. You get this linear dependence. Now, miraculously, it's not only the mass, it's all couplings of this axion to standard model particles are proportional to 1 over f. All couplings, okay? So, for instance, in this plot, actually, it's the coupling of the axion to photons. But this coupling is proportional to 1 over f. So it has units of inverse GeV. And m is proportional to 1 over f. So m is proportional to this coupling, which is why you get this linear dependence. So this is a very beautiful framework where we get a very light blue particle that's naturally light and naturally very weakly coupled. In fact, if you crank up f, it gets lighter and lighter, and it decouples more and more from the standard model. So it's a prime candidate for a weakly coupled particle. You don't need to do anything to make the coupling small, just make f large. And in fact, this is also a dark matter candidate. This is a candidate for even arbitrarily light dark matter. Even, you know, I showed you yesterday, it can go all the way to 10 to the minus 22 electron volts. An axion could in principle do that. I think on the plot here, it goes to 10 to the minus 9 electron volts, but you can just continue. This band will continue forever. Of course, the more weakly coupled it is, the harder it is to find these axions. So there's some experiments here that, you know, you see it's hard to get to really these extremely small couplings, but it's not so hard to get in this mass range. Sub-electron volt, but not extremely small. Okay. So that's the classical axion. It's the solution to the strong CP problem, and it's an example of a class of models where you have light blue physics with weak couplings natural. But theorists are very inventive, right? So you know, you are on this yellow line, and then you say, well, you know, but it's very unfortunate that it's so hard to measure. Can we not move this line a little bit up so that we have more hopes to measure this thing? And of course, the answer is, if you try hard enough, yes, you can. So this is what one calls axion-like particles. Axion-like particles share all the features of axions. In particular, they rise in spontaneous symmetry breaking. Their couplings are still inversely proportional to a high mass scale, but their mass can be the relation between the mass and Fa in the flux. You can soften up this relation that the mass can be higher or smaller than the yellow band I was showing you. There's a lot of work that actually goes back to many decades ago, but even in recent years, I guess several papers addressing that.
You want them to still solve the strong CP?
That is also an open question. I think for axion-like particle, people don't insist that it solves the strong CP problem. But again, if you were to find such a particle, for sure, within a week, you would have 20 models where it also solves the strong CP problem. So people are in that sense, people are very inventive when it comes to model. But for the purposes of this talk, I'm not assuming that it necessarily has to solve this. So basically, you know, these axion-like particles, they're just what we call pseudo-number Goldstone bosons. Their number Goldstone bosons are light degrees of freedom arising in spontaneous symmetry breaking, and the word pseudo means they get a small mass of some explicit symmetry breaking. And they arise in the large class of models beyond the standard model. Almost any model beyond the standard model gives rise to such like pseudoscalar bosons. So it's a generic possibility that follows from model building. And the question is, you know, we can perform these astrophysical experiments to looking for these very, very light pseudoscalar particles. But the question is, can we also look for light pseudoscalar particles in particle physics? Now, in particle physics, we talk, the units are more closely GeV than electron volts. And the question is, you know, is there any interesting parameter space where it would be worthwhile to perform experiments to look for these particles? And the answer is, or was a couple of years ago, well, you know, there's all this parameter space up here for masses heavier than an MEV, let's say, MEV, GeV, TeV. Okay, so somehow in this mass window, we could look for these particles. That would be interesting. Down here, it's cosmology and astrophysics that provides the most interesting things. And in particular, you know, when we started working on this about 7 or 8 years ago, this range here, this parameter space was completely unprobed. Now, I want to be completely agnostic as to the properties of this particle. I only assume that there is a shift symmetry. So I told you the axion is essentially the angular degree of freedom in this Mexican head potential. The minimum of the potential builds a circle, and it's the angular degree of freedom that lets you move in this circle. So if you add, so A is the phase really, if you add to this phase a constant amount, the physics doesn't change. It's like a gauge transformation. So, you know, you introduce a light pseudoscalar particle to the standard model and require that the Lagrangian is shift symmetric, with the exception of the mass term. So the mass term breaks the shift symmetry in explicit way. That's a small perturbation, but the rest of the interactions is shift symmetric. And then what you find, that's already interesting, what you find is you cannot have this thing interact with the standard model at the renormalizable level at dimension 4 in the Lagrangian. All the interactions are suppressed by the scale 1 over f, and they are of dimension 5 or higher. Okay, so these are higher dimensional interactions. There's nothing bad about them. It's an effective field theory. Okay, so this is valid under this for energies less than this large scale f. And then you can write down, this is the most general Lagrangian at order 1 over f. There are higher order terms at order 1 over f squared or 1 over f cubed. We assume there's some.
Can answer question? Would you like to be take more than one scale sensitive or relativity method? Cancer questions that is for in the earlier slide. Do you like if we take more than one scale instead of one scale?
What do you mean by taking more than one scale?
Not for that, actually, but for the ALPs, can we have like independent or two?
There are models with more than one ALP, and then each can have its own F scale that exists actually. If that was your question, I'm not sure.
But for one ALP, there would be only one.
Well, in some scale, okay, so let's look at this. So for instance, for the axion itself, what you care about is the coupling to the gluon field, and that F is what people used to call FA. And now instead of FA, I call it F, but I give a dimensionless coupling here, CGG, which is the coupling to gluons. And now you see I get a coupling to the SU2 gauge bosons of the weak interaction, a coupling to hypercharge, a coupling to the Higgs, and a coupling to all the fermions of the standard model. So in some sense, you know, I could, instead of putting these dimensionless couplings, I could call this F gluon, FW, FB, Fx, and F fermion. So in that sense, you could give a coupling for each particle type. But I introduce one F to set the dimension side, and then all the couplings are dimensionless. It's equivalent. So this is the most general Lagrangian. We call this an effective Lagrangian. We just write down everything that respects the symmetries. The symmetries here are the ones of the standard model. And all I do is I add a pseudoscalar to the standard model. And this Lagrangian is shift symmetric. You can see here where I write a derivative of A. Obviously, adding a constant to A doesn't change anything here. For the terms in the second row, that doesn't look like it would be the case. Because if I add a constant to A, it looks like I add this contribution, I add a constant term, but you need to remember that the field strength of a gauge field times the dual field strength is a total derivative. So adding a constant here actually, with this being a total derivative, doesn't change the action. The only place where it does is in QCD, and that's precisely what you need to cure the strong CP problem. Right? So this is the right way of adding this axiom to the gauge. Good. So now how can we search for these particles? Okay, so we can search for them directly and indirectly. Yesterday, in fact, in the middle of the talk, I mentioned that when we look for physics beyond the standard model, there's always this direct way trying to produce a new particle and indirect way trying to look for quantum corrections from the presence of hidden particles. For the axion-like particle, it's the same thing. We can do direct searches and indirect searches. Let's ask about direct searches, and I should stress again, in the context of particle physics. There's many other things you can do looking for very light axions, but I'm interested in particle physics searches for axions. If you want to do direct searches, you can immediately see that it's going to be rather model dependent, because I need to first produce an axion-like particle, and then I need to reconstruct it.
The fermion couplings or flavor diagram?
The fermion couplings, no, thank you for asking that. The fermion couplings, there is a boldface here, but it's hard to see. This in general, this is a Hermitian matrix in flavor space. They're not diagonal. And in fact, we will come back to this in the second half of the talk. It's very interesting to look at flavor effects. There's no reason for it to be diagonal, but in order for the Lagrangian to be Hermitian, this thing to be real, this needs to be Hermitian.
And if I imagine there's a U1 and I give each fermion a charge in the flavor basis, then it will be that.
And then you can make it diagonal, but then you add a flavor symmetry. Yes, absolutely. Okay, so here my point is that I need to produce the axion-like particle, and then I need to reconstruct its decay. And in general, the production will be in a different channel than the decay. Okay. So, for instance, an interesting search channel is this one, where you use Higgs bosons to decay to a pair of axion-like particles, and then each axion-like particle decays to 2 photons. So you would have a decay of essentially a Higgs to 4 photons through this axion-like particle. Why am I using Higgs decays? I mean, the problem is at the LHC, you produce a zillion of particles. So somehow, in order to perform a search for something rare, you need something to trigger on. You need something that is kind of a candle that you can look at, and the Higgs is one of those. The C boson is another one that you could use for similar purposes. But now you see the
Higgs can have a marginal or operator with the X.
No, they don't.
H square is square.
It's not shifting direct.
Well, you have given M square S square.
I have introduced the mass, yes, but that is supposed to be the only.
If you like the H square cosine, right? So in general, you could write a marginal term that can have its way.
I don't think so.
Only if you break shift symmetry.
It would break the shift symmetry. You know, I want to break the shift symmetry only by the mass terms, the only square. So I can have a term MA square, X square, A square that I could do. That would be dimension 6. Or I have this dimension 5 interactions.
Which is giving the H to AA in this?
Actually, it's a term of order 1 over F square, which I didn't write down here. Okay, so we can have this coupling, and then in the decay, we have the outcoupling to photons. Okay, so you need to keep this in mind. this is a general problem of the ALP literature, that almost always people show results in terms of one particular coupling, but you always have to keep in mind that assuming that only a single coupling is present, for instance, is a very strong assumption, and sometimes the second coupling is a little bit swept under the rug, simply because it's easier to do two-dimensional plots than three-dimensional plots. So at the time where we wrote this paper, there was still an anomaly of the anomalous magnetic moment of the muon, which since has disappeared. And in fact, the red band here showed the parameter space where an ALP could explain perfectly this anomalous magnetic moment of the muon, and that parameter space was in this white region here. So basically, at the time, we tried to exclude this region, or look for ALPs in this region where they could explain G-2 of the muon. And it turned out that this process can very well do so. Of course, this is independence of the ALP photon coupling and the ALP Higgs coupling, so I cannot show both at the same time. So we plot the ALP photon coupling here, and the ALP Higgs coupling is very T over 2 orders of magnitude, and it basically defines the left corner of this parameter space. So everything to the right of these lines is excluded up to the point where the ALP can be produced in this decay. So half the Higgs mass, basically, whatever, 60 GeV. So basically, we concluded that almost all this white parameter space can be excluded if the Higgs coupling is not much smaller than what is shown here, and over a wide range of ALP photon coupling. So actually, a colleague of mine in Mainz, he got an ERC grant for doing this measurement, interestingly. And he has performed this measurement in the Atlas collaboration, and it was published about a year ago. No, actually Christmas 2024. And this is what they exclude. Everything left to the right to the supernova and beam dump constraints, which are here in our case. So basically, it's a little bit worse than what we estimated, but not much worse. And the reason is that we assumed a higher, we assumed 300 inverse femtobarn, and they performed the analysis with 140 inverse femtobarn. But you see that it goes down here to 10 to the minus 7 in the photon coupling, which is exactly what we had predicted. So basically, they confirmed this analysis, except
to one of axion photons.
So axion, the A2 gamma gamma.
Oh, the A2 gamma gamma. Yes, you are right. This is a third thing that's in our paper. We discussed that in detail. Of course, the question is how big is the branching ratio A to 2 gamma, and that shifts these curves, but actually on a log-log plot, not in a very significant way. You know, as long as this branching ratio is not 10 to the minus 3 or 4, then it doesn't have a big effect. But you're absolutely right. That must also be included. But actually, the branching ratio is not so important because there's an interesting compensating effect between of course, the decay scales with the branching ratio, but the lifetime also. And this limit here is really set by the fact that at a certain point, this thing becomes too long-lived to be reconstructed in the detector. And there is a cancellation that actually the branching ratio to first order cancels out there, that if the branching ratio is smaller, then there are some other decays, the thing becomes shorter lived, and the chance to reconstruct it in the detector is higher. So actually the position of these lines stays fixed as you change the branching ratio, but the number of events that you find scales with the branching ratio. And in our paper that it's explained that, you know, there's a certain minimum branching ratio for which you don't find it. Okay, so I thought that was a sort of a cute thing. They made a big fuss about this, that they improved the bounds on the photon coupling by many orders of magnitude compared to previous Atlas constraints. As you can see here, you go down by 5, 6 orders of magnitude. But the caveat is that it is under the assumption of a certain coupling to the Higgs boson. But it's a very cute analysis. Now I want to come back to your point. What about the fermion couplings? Can they be interesting with regard to flavor physics? And the answer is, of course, yes. And actually, you can do these very simple weak decay processes to probe the ALP couplings to the fermions. This is something like a semi-leptonic decay, where you would have a W boson and a lepton-neutrino pair here, but instead of the W boson, you emit an ALP. Okay, and we can look at these two particle processes, kaon to pion ALP or B meson to kaon ALP, and we can put constraints on these couplings. Now, of course, these decays on shell are only allowed if the ALP is relatively light. So for instance, here, lighter than the kaon minus pion mass, or here lighter than the B meson minus kaon mass. So we are in the sort of GeV, sub-GeV region. But you will see, in particular from this first decay, that we will get extremely strong bounds, actually, by far the best particle physics bounds one can get in that low mass region here. So it's actually very interesting. And of course, again, here we would produce the ALP through a flavor changing interaction, for example. But then again, the question is, how does it decay? Does it decay to photons, to leptons, etc.? So again, it's a multi-parameter phenomenology that one needs there. So here, what we do in a first look at this is we really place bounds on this flavor changing ALP coupling. So here, of course, is where a heavier quark decays to a lighter quark under emission of an ALP. It's a flavor changing ALP coupling. And here I'm looking at various flavor changing decays that have been measured in the kaon sector, in the B sector to pions, B sector to kaon, and charm mesons to pions and kaons. Just look at all of these experimental results and you recast them under the assumption that an ALP was emitted. So for instance, in modes where I see K to pi gamma gamma, I can look, is there a resonance structure in the diphoton spectrum? And then I could interpret this as an ALP produced decaying into 2 photons. Or I can look at kaon pion 2 neutrino, 2 muons, and I could look, is there a resonance peak in the muon spectrum? And I produce an ALP decaying to 2 muons or to 2 electrons. Okay. So this is the decay mode. There are also searches, dedicated searches for kaon to pion plus nothing. That would correspond to an ALP that leaves the detector before it decays. So, you know, depending on what has been measured, you constrain ALPs that are invisible or decay to photons or decay to leptons. And then the coupling is always constrained up to a factor of the square root of the branching ratio into that final state. And you see that in kaon physics, you constrain obviously the first to second generation flavor changing couplings. In B physics, you constrain the couplings to the third generation. And in charm physics, you also constrain the couplings of the C quark to the S quark. Or C quark to the U quark, second to first generation. And the bounds you get they're shown here in inverse TeV, and they're very strong. You see that the numbers here are 10 to the minus 9, 10 to the minus 8, 10 to the minus 7 in that range. And it's better to think of these bounds, to take the inverse of this. That would give you the scale F associated with these transitions, and that is the new physics scale. So we are talking here of scales of order 10 to the 5 to 10 to the 9 TeV. Okay? You see that these are very sensitive searches.
If you assume that these couplings are diagonal in the flavor basis and they're only rotated by CKM.
Excellent point. That will be the rest of the talk, basically. Yes, exactly. So this was agnostic. I'm just asking, what about these?
So the other way around. I want to be completely agnostic in the sense that I will actually have a flavor, biological couplings in the flavor basis, so that when you do a rotation into the mass, the size you can start, right? So that the off-diagonal elements, but at the end of the day, you're doing the rotation at a very low.
I will discuss all of that. That's not possible because the ALPs have emission couplings. It's not the same thing. You cannot rotate them away easily. But I will discuss that. Okay. So in order to discuss that, I need to do precisely this. I need to do effective theory renormalization group running, because really we have a multi-scale problem, right? So we have our Peccei-Quinn symmetry breaking at a high scale 4 pi f that we assume is above the standard model. And above that is some unknown theory, okay, a theory which has these new complex scalar fields with a new Higgs potential that creates the symmetry, etc. We don't know what that is. We're agnostic here. Below the scale 4 pi f, we have my effective ALP Lagrangian that I showed you earlier. And then we can run it down to the standard model. Standard model, we have the electroweak symmetry breaking. And of course, through the electroweak symmetry breaking, we inherit the weak interactions of the standard model, which also change flavor. And then we can run down to whatever the scale is that is relevant for the experiment. In the case of B-meson physics, that's the B-meson mass, 5 GeV. In the case of kaon physics, actually we match here to a chiral Lagrangian at a scale of order, let's say 1 or 2 GeV. Okay, and that has been studied in 2020 by our group and also by the group of Chala, Guedes, Ramos, and Santiago in Granada. So now, of course, if I showed you these very strong bounds, 10 to the minus 9, 10 to the minus 8, the first thing you would say is, well, okay, let's impose a flavor symmetry and try to make this coupling simply flavor diagonal. And of course, we can do that up here. We can do that by imposing a flavor symmetry. But we cannot avoid that when we come to the standard model scale, to the weak scale, and we integrate out top quarks and W bosons, we necessarily, this would be the flavor changing ALP. We can avoid this. But we cannot avoid this. This is an ALP coupling to 2 top quarks, and then it's the W boson that gives us a flavor change, or an ALP coupling to Ws, and now it's this diagram that gives us the flavor change. So if the ALP couples to even diagonally to up-type quarks or to SU2 gauge bosons, and that we really want because we wanted coupling to the photon usually. So you get necessarily these flavor changing effects. And that's what we call the minimum flavor violating ALP, minimum flavor changing ALP. In the UV, it's flavor diagonal, but then we inherit these flavor changing interactions. And you see it's minimal flavor violation. It's this VTI, VTJ that is familiar from minimal flavor violation. And you get this from the ALP top coupling, that's this diagram, from the ALP coupling to Ws, that's this diagram, and you also get it at 2-loop order from the ALP coupling to gluons. So you couple the ALP to gluons, the gluons couple to a box of fermions, and then you 2-loop order. You get a contribution from the gluon, and I mean an ALP that would not couple to the gluons, it wouldn't be an ALP, I would say, because axions are defined through their coupling to gluons. That's what makes them an axion. So this thing is completely unavoidable, but in the canonical models for axions, you often have couplings also to the fermions or to the SU2 gauge bosons. So you get this flavor change whether you like it or not. And now you can play the following game. You can look at minimal benchmark models where you say, in the UV, I switch on a single ALP coupling at the time. And now I do this RG evolution. I generate all the other ALP couplings, or most of them, through RG evolution. And then I see what the phenomenology does. And I could show you for each coupling, could show you a plot like this, but I will only show you this one plot. And the others look very similar. So what I do here is I switch on a coupling to up-type quarks in the ultraviolet, flavor diagonal. And then I do this RG evolution, and in particular, it generates flavor changing interactions. And you see now, if you look at the bounds that you get on parameter space, you see that the strongest bounds have to do with flavor. Okay. So for instance, this is the B to K, neutrino, neutrino, K to pi, neutrino, neutrino. They give you bounds that reach down very deeply here, 10 to the minus 3, 10 to the minus 4. This is K to pi, it's also flavor. This is B to K ALP, it's also flavor. All of these are flavor. This is flavor diagonal. And there are some things here which are flavor diagonal, but all of the most sensitive bounds come from flavor violating decays, even though I assumed flavor universal ALP in the ultraviolet. And as I said, I could do the same thing for other couplings. It would look very similar. Now, particularly interesting is this decay, as you can see here, that gives the strongest constraints in the region where it's kinematically allowed, below about 100 MeV. And there's an interesting story that this decay was analyzed in 1968 in this paper by George Kaplan and Rendell, where also they wrote down for the first time this effective Lagrangian for the ALP. But actually, for 40 years almost, people didn't realize that actually this implementation of the Carrel Lagrangian was not done correctly in this paper. And we corrected this only in 2021 and found a factor 40 change in the branching ratio. But actually, it was simply an error. So the error could have been an order 1 error or order 100 error, or something that needed to be fixed. Okay, so we fixed that here. We got the strong constraints that I showed you earlier, and then we carried out this chiral analysis at next to leading order, because wanted it to be a bit more precise. And actually, that turned out to be an interesting topic for a PhD thesis, because it was not a trivial calculation. We'll show you some diagrams. And we also discovered that there are some couplings there are many couplings in the chiral Lagrangian that come in here, and that are either not well known or not known at all. So there is some uncertainty also, simply from the fact that chiral Lagrangians in higher orders contain many low energy constants, which are not very well constrained. This is the bunch of diagrams you need to calculate. All these diagrams are trivial to evaluate, but the point in the chiral Lagrangian is you get many terms. So bookkeeping is an issue, but nothing that cannot be dealt with. But this was together with Claudio Cornella and my graduate student Anne Galda and Daniel Wieler in Zurich. And that's what we found, basically, just to illustrate. What one finds is the next to leading order corrections have rather large uncertainties, basically order 1 uncertainties from these low energy constants, but seem to be under control in the sense that they are significantly smaller than the leading order terms. So compare here a coefficient of order 2 at leading order, and then a coefficient of order, whatever, 0.2 with a large uncertainty at next to leading order. Similar here. Other example. So for all couplings, it looks similar. The next leading order corrections have large uncertainties, but are not overwhelmingly large in absolute terms. Okay, so with this analysis, I should have stressed the most important thing is the following. you get contributions in this analysis from really flavor violating ALP couplings in the effective theory at low energy. And I told you they are necessarily there from Archie evolution. But actually, even if these couplings, even if you ignore these couplings, the decay can still happen through the weak interactions of the standard model. So actually, you also get contributions from flavor conserving ALP couplings at low energy times a weak interaction in the chiral Lagrangian itself. And therefore, one really needs to take both sources of possibilities into account with the reliable pheno analysis. What we did before was a bit simplistic. So before we just cared about the first line, the off-diagonal ALP coupling. This is now at low energy, and I reproduce what we had before, bounds of order 10 to the, here I show the inverse of the coupling, bounds of order 10 to the minus 9 before, now the inverse is 3 times 10 to the 8 TeV, that's the new physics scale, if you wish, associated with this off-diagonal coupling. And then you also constrain the coupling to gluons, new physics scale of order 40 TeV, and diagonal couplings to fermions with new physics scales of order several TeV. Okay, so all these couplings can be constrained in the multi-TeV range from this 1 decay K to pi r. Very interesting. Actually, the first line, if you do not impose a flavor symmetry, the first line is maybe even problematic, because 3 times 10 to the 8 TeV, if you transform it to a value of f, you get something like 10 to the 11 TeV. And there are some papers from string theorists and cosmologists which argue that f should not be bigger than 10 to the 10 GeV. This has to do with topological defects in the early universe, and it's not model independent. It has to do with whether the Patrick-Winn, at which point the Patrick-Winn symmetry breaking occurs. But I just put this here. This is from this paper by Gorgetto et al. I just put this here to show that in this weak decay, one is sensitive to mass scales, which actually can, be of relevance even to cosmological aspects of ALPs in the early universe. But then, as we said earlier, if you think this is frighteningly large, just impose a flavor symmetry and see what you get. So this is now in the minimal flavor violating ALP scenario. Now the bounds are much more relaxed, because in the UV I switch off all flavor changing couplings. But you see, you still get interesting bounds. These are now bounds on the ALP coupling at the new physics scale 4 pi f. For the purposes of this table, I take f to be a TeV. And then you see the bounds are still very interesting. On the gluon coupling, 50 to 100 TeV. On the W coupling, a few TeV. On the up quark coupling, 2000 to 4000 TeV. Still very powerful. And on the down quark coupling, 50 to 80 TeV, depending on the ALP mass. Okay. So you see that this simple harmless decay K to pi ALP, it really constrains these ALP couplings, all of them, even in the minimal flavor scenario, it constrains them in the multi-TeV.
So the C theta is 100, so I should put it 100 over 1 T.
So the coupling is 1 over 100 TeV.
So C theta was a numerator, no? Look,
so this lambda is f over c. It's the inverse. I like more to think in terms of mass scales than couplings. So this means that, here I assume f1 TeV. This means the coupling must be smaller than 1 over 50. Which is a strong bound on the C bound. And this shows how things depend on, so how these lambda parameters change with f, and they change logarithmically. It's just from the RG running. And I assumed 1 TeV here. If you want a larger value of f, you get a small running of these values, but not very significant. Okay, now I forgot when I started. Probably my time is probably almost up. I can either stop here.
You can take 5, 10
Okay, if I can take 5 more minutes, that's all I need. I wanted to briefly talk about indirect ways of the ALP couplings, because I think this is actually an interesting technical point to make here. So indirect, what I mean is that we are not producing the ALP anymore. We're looking for quantum effects of ALPs. And at the time, again, there was still a puzzle with the electron anomalous magnetic moment. So this is the first thing we calculated, contribution to G-2. And it comes from this diagram and similar diagrams at one loop order. And the point in this diagram is that I told you any interaction of ALPs with standard model fields has a 1 over f. So this one loop diagram necessarily has a 1 over f squared. And then it has a loop function. The loop function will depend on the new physics scale divided by the ALP mass scale. So there's a large log here. And then there are non-logarithmic terms, okay? But this is the largest contribution, is this large log. And now the question is, what remains after I write this factor here? What remains is what you get by basically shrinking this loop diagram to a point. And then you get a local coupling of the photon to muons. But because there is a 1 over f here, this must be the matrix element of a dimension 6 operator, not a renormalizable operator. And those operators, for those, we have a framework that we call SMET, the Standard Model Effective Field Theory. So what I show you here is, even though I have a light new physics particle, when I compute its loop effects, because of this 1 over f suppression of the couplings, I'm generating a contribution in this SMET. That's not what you would naively expect. Naively, SMET is built for heavy new physics that you integrate out. But because of this 1 over f squared, this contribution here must be a matrix element of a SMET operator. So actually, what that means is if you want a consistent ALP effective field theory, we have at order 1 over f the interactions with the standard model for the first time. This is the term relevant to direct searches. If we want to perform indirect searches, we get effects at order 1 over f squared, but then we generate operators of the SMET, not of the standard model. And in fact, what these loops do, they contribute in homogeneous terms to the RG evolution equation of the SMET operators. So basically, the running of the SMET operators has been studied in the literature, is described by the left-hand side of this equation equal to 0. But now with an ALP added to the standard model, the 0 gets replaced by what we call an ALP source term divided by 4 pi f. So we can now, from the Lagrangian I gave you earlier, we can compute all these ALP source terms. And we find that almost all of the SMET dimension 6 operators are generated by ALP effects. And now we can do a very beautiful thing, because people perform global fits for SMET coefficients. They basically take all precision data that there is, top quark physics, Higgs physics, electroweak precision observables, flavor physics, you name it, electric dipole moments, magnetic dipole moments. We can take the results of this global fit for the C coefficients, and we can make the assumption that we have standard model plus ALP. And in that scenario, in that minimal scenario, what does it tell us about the ALP couplings? And we have performed such a fit together with Anke Biekötter, who is an expert in ALP fits, and Javier Fuentes Martin, who has implemented this SMET running in a nice Mathematica package. And this is what we find for, now we work again in a flavor minimal scenario, where you just have ALP couplings to gluons, Ws, hypercharged, up quarks, down quarks, electrons, everything flavor universal. And then you can do the usual game, either you fit one coupling at a time, or you perform a combined fit to all couplings at the same time. That's the difference between orange and blue. If you look at the global fit to all couplings, it's the orange values. And what you see is that, again, you constrain these couplings at a level of about an inverse TeV up to weaker constraints on the electron coupling and the down quark coupling. But the couplings to the up quarks and the gauge bosons are constrained at more or less an inverse TeV, which is not as powerful as what I showed you before, but the advantage here is that this is largely model independent. I don't need to assume how the ALP is produced, how it decays, what its branching ratios are. That all doesn't play a role. It's really just the couplings entering in these loop diagrams. So these bounds, in the context of this scenario, standard modulus ALP, are completely model independent. And they are also largely mass independent. And what I compare here in gray is the direct bounds I showed you earlier, and in red is these indirect bounds. And you see where the direct bounds are very strong, they win. But there's regions where the indirect bounds win because we simply don't have good constraints. So for instance, when the kaon physics and the B physics runs out, we don't have very powerful constraints on the ALP couplings, and then these indirect constraints become more powerful. So there's a nice complementarity.
So what gives you the electric precision?
It's the global fit. I cannot, in the paper we have a lot of detailed correlations where you can answer that question, but it's the result of the global. But whatever constrains the SMET coefficients most also gives these more detailed answers. So that's really now the end of the talk. So I think, since we're not lucky enough yet to find new heavy particles that we can study in detail, we can try to search for light new physics. And at least axions and axion-like particles are well motivated. First of all, they appear in many concrete models, and they could be linked to the problem of strong CP. So it's a well-motivated study. Many people have looked at this in recent years. There are interesting search targets also for measurements in high-energy physics, using collider constraints, flavor constraints, and precision probes. And in particular, flavor plays a very interesting role here and gives rise to the strongest constraints in the regions of masses where these decays are allowed. And the indirect searches, which are briefly covered in the end, are a completely alternative way, less sensitive a bit over most of parameter space, but completely model independent and complementary. And of course, it would be wonderful to find such an ALP in the future, but we have to be patient. So with that, thank you very much for staying here.
Two questions. So, when you showed this plot of this ALP interacting with the SMET operators and interacting the bond with the SMET global physics. So, we actually need this, at least two ALP couplings to be non-zero.
I'm not sure. For instance, here the situation is not, this is not necessarily so. So for instance here, okay, I see what you say. So here I have the ALP coupling to the photon and the ALP coupling to the muon, but actually there's a second diagram where you have there's a second diagram which is this. Photon and then the ALP going this way. where you will couple twice to the muon. So for these loops, you can have both. I mean, of course, in many diagrams, more than one coupling, but there are also contributions with just single coupling. So also, for instance, if I look at the S and T parameters in the electroweak fit, I could, if the ALP couples to electrons, for example, or to Z bosons, I could just use that one coupling. Like a one loop contribution there.
And one more thing, like, you will, when you constrain this algorithms from the, their meson decay, can you also look into the angular distribution to,
Yes, you could, but the decays I looked at here were very simple. This was K onto pi on ALP. There is no angular distribution, right? So it's two-body and not even a vector meson involved. So, but in principle, you are right. And in particular, if I, for instance, if I look at K to pi gamma gamma, when the ALP decays to two photons there, of course, you can look at them. Yeah, I mean, obviously, if you would find something, that would be the first thing to do to, for instance, ask the question, is it a pseudoscalar or maybe a scalar or maybe a vector resonance or something like that. So then you need to look at angular distributions, figure out the spin path there. Absolutely.
Some of this, like if you buy A, there are flat directions which just the rate to get by A does not get covered. In multiple couplings, you could come up, there are flat direction where you can get cancellations between these that don't get through. And in those cases,
Yes,
like
distribution. I mean, this was a very unfancy analysis in a way. Really, the simplest thing. You're absolutely right. Yes, certainly both. And you're right. There are flat directions. I mean, I showed you, which was also the interesting thing here. I showed you this. You know, this is the four couplings that enter actually in this decay rate K to pi ALP. And of course, at the amplitude level, if you're unlucky, you can have, there are flat directions, which is another way to say that if you play with the sign and magnitude, you can have these effects cancel. I mean, often one assumes that one at a time is dominant and then you would bounce on one coupling at a time. But yes, you are right. It's contrived.
so we need to express gamma. So that the charge. So coming back to this, thinking how exactly the action of that for
Yeah, B2S gamma, we looked at briefly, we didn't find a big contribution. Because it's an inclusive decay, so it's not very easy to recognize an ALP there because it's inclusive, right? In the final state, you can have K star and 3 pions or whatever, photons, leptons, it's all inclusive. So it's probably not a very good way. A little bit more sensitive BB bar mixing or KK bar mixing. We also looked at that.
In that case, can exclusively be helpful?
Exclusive is more helpful for these purposes. You really want to identify all the final state particles. You don't want to sum over all possible final state particles. But I think I had this earlier here. So, for instance, this is from this gray region is from BB bar mixing. At very high masses, that is interesting, and also here there's a small slice left from this. But in general, here there's another one that is not flavor changing, upsilon decayed photon plus invisible ALPs. But in general, the flavor changing things, when they are allowed kinematically, they give them more powerful parts.
So, of course, collateral constraints. How do the astrophysical constraints measure?
I think they're really completely orthogonal. I don't know what is probably my first plot. is an interesting one to show this one maybe, or even before. So you see, if you do particle physics searches, you always, no matter what you do, there's always going to be this cutoff here, which is simply the place where the ALP becomes long-lived. If you go to the left here, the rates become very small, the lifetime becomes larger, and at a certain point, this particle has macroscopic decay lengths. 5 meters, 10 meters, whatever is beyond the LHC detectors or the relevant parts of the LHC detectors. And then if you go to the left, it can become of galactic size, if you like. But there's always going to be this line. So to the right of this line is where the particle physics detectors are very powerful. And then it's completely irrelevant for astrophysical things, because you want things to fly from the sun to us, or from, you know, from the center of the galaxy to us in order to see them. So in a way, it's decoupled. You know, when they're long-lived, it's astrophysics and cosmology, and when they're short-lived, but
Short you could do 2 photons.
now, like for instance, let's say you have in the middle of the sun, you produce ALPs, and you want to derive a bound by supernova explosions, the cooling of the supernova, where all these ALP emissions. If the thing decays after a few femtometer, it won't have an effect, right? So
Also the mass, the temperature, the mass has to be smaller than the temperature.
yes, So I think it's largely orthogonal. We can really draw this diagonal line and say to the right, it's more in the particle physics realm. Actually, the one thing that I didn't put this slide in, but the one exception actually comes from K2 pi ALP, because in K2 pi ALP you can make the ALP masters. In principle, you still get the same bounds. And now these bounds are, if you compare them to the astrophysical bounds on the photon coupling, you go down to 10 to the minus 7, 8, 9 or so, much more sensitive. But actually, if you look at the ALP couplings to nucleons, proton and neutron, they're not so sensitive. And there actually we showed that the bounds we derive from this work on kernel physics, even for very, very light axions now, are competitive with some of the torsion pendulum Casimir effect type of bounds that one gets. So actually this is the one coupling where even for massless axion, or for very light axion, we are sort of competitive with other. But those are also not constrained by astrophysics. Those are constrained by tabletop precision experiments. But that is an example where we can really go to very light ALPs, and longevity doesn't play a role, because this is the mode where the ALP is invisible. It's like a neutrino. It's just missing energy.
What about the nuclear sector? I mean, there have been many attempts, not many, but some attempts to look for such as like particles in the decay of nuclear excited states from 0 plus to 0 plus.
So, as I said, unfortunately, I don't have that plot in, but we have the couplings to the proton and the neutron, and maybe I can show you after the talk, but it's unfortunately not in the talk.
So here you have taken a far more relaxed definition of ALP in a sense compared to axion, that added the mass and generalized the couplings to all the quarks and matters. People have somewhat gotten even beyond that, right? I mean, you have ALP sort of total into dark sector and stuff like that. I mean, most of these bounds, like astrophysical bounds, goes away if you say axion have decays to dark matter and stuff like that.
Yes. So that's the point I made earlier, and it's unavoidable in this game. But also the astrophysical bounds are not model independent,
right?
Because you typically assume single coupling and nothing else. And as you say, if there is if there is a dark sector, you can always write A over F, or you can always write a coupling. For instance, if you have a dark fermion, just take psi bar gamma mu psi and couple it to d mu a, and you're there. Right? So this coupling.
So all constraints from sun goes away. It is strong enough coupling with dark sector.
And also allowing for coupling to electrons invalidates some of these bonds, because the interactions in the interior of the sun or in the center of the galaxy, they would change, of course, in that way. So actually, we made this point also in our papers that these astrophysical bounds are not so innocent. You really have to look very carefully at what the assumptions are.
And in fact, there is no alternative to lab probes for this kind of scenario.
Yeah. Well, I don't know if I would go so far, but you could go so far, because one point of this paper on RG evolution was that even if you start with, let's say, only a coupling to photons in the ultraviolet, you generate couplings to fermions through RG evolution. And electron coupling could be a problem for this aspect.
Look, I mean, if you have two unknown couplings in the tree level, and whatever you do, you still have two unknowns. So you can say, well, it is not generic, it's not most agreeable, but
No, I think we agree on that.
Yeah.
Okay, so if there are no more questions, let's thank.